GPT from OpenAI, Gemini from Google, and LLaMa from Meta are all examples of LLMs or large language models. In this video, we'll be understanding about the transformers which made these LLMs possible. We'll also be covering different aspects of transformers, including the self-attention behavior. Later, we'll see what is prompt engineering and how it helps us in training an LLM model. We'll discuss more about it in detail in the second part of this video. So let's get started.
Okay, so this is the typical flow diagram of our transformers architecture taken from the groundbreaking paper Attention is All You Need, which was published in 2017 by the researchers at Google and University of Toronto. Now at first, the architecture looks really complicated, I know. But don't worry, we'll go step by step, understanding the intuition behind each of the components in our architecture. First, let me simplify this for you. So on the lower side, you see the inputs which are being fed to our architecture model, while on the upper side, there are outputs which are being provided by our model. Now we'll start with the lower side, which is the inputs. Let us assume this sentence. Now machine learning is all about statistics and numbers. It could not understand any words given in any form of languages to it. So in order to make it compatible for our model, we need to first convert these words into some form of numbers. For that, we use tokenizers, which map each of the words to a unique number, also known as token IDs. Now these token IDs represents the position of the word in the whole English vocabulary. Now once we have our token IDs, we provide these token IDs to the next component, which is the embeddings. Okay, we know we have our token IDs which represent each of the word in our whole English vocabulary. Now these token IDs still doesn't know what is the meaning behind that word. So in order to do that, what model does is it embeds these token IDs into a unique embedding vector which is in a high dimensional space. Now in our original transformers paper, this space is of 512 dimensions. That is, the vector is of 512 rows. Now it is impossible to visualize this vector in a high dimensional space. So for simplicity, we'll take a 3-dimensional space to understand how it embeds these vectors. So let us take an example where we have words like books and pencils. These are mapped to a certain positions in this space, and we will observe that these points will be mapped to a closer proximity when compared with words like books and oranges. Why is that so? Because books and pencils have higher chance of coming together in a sentence than books and oranges. So the contextual meaning of books and pencils will be closer as compared to books and oranges. Now these embedding vectors could either be pre-trained or could be tuned while training the whole architecture. Some examples of pre-trained embedding vectors are word2vec, which you can look upon internet if you want to know more about it. Once we have our unique embedding vector, we go on to the next component of our architecture, which is the positional encoding part. Now let us see this sentence. Each word has a unique embedding vector which provides a meaning to the model. What if I take another sentence which is just the rearrangement of the words from the first sentence? Now in this case also, the embedding vector would be same as for this first sentence. So how would model differentiate between the two sentences? Because we know that these sentences are completely different to each other, but the model still doesn't know it. So in order to incorporate this position information, the model adds another vector to the embedding vector, which is the position embedding vector. Now these position embeddings are calculated based on some sine and cosine functions of the position of our word, and then added to our unique embedding vector, which gives a final vector and which is passed to the next component, which is the encoders and decoders to our architecture model. Now before moving on, I would like you to notice there are two major parts to our model, which is the encoders and the decoders. What encoders does? So the encoder is responsible for understanding and extracting the relevant information from the input text. So it takes in the input text, extract the informations and provide it to the decoder. While the decoder task is to generate the new text that we want to generate. So this is one type of transformers that we see. We have transformers that contain only decoders or only encoders. But here we will look at encoder-decoder type transformers. Okay, now we can move on understanding each of the components inside encoders and decoders. So the first component is that of self-attention behavior. Let us take this example again. Now, before transformers, we used to have RNNs or recurrent neural networks for natural language processing. In RNNs, every word is predicted based on the previous word in the sentence, and that is how these words are related to each other sequentially. But after transformers arrived, everything changed with this self-attention behavior. In self-attention, every word is related or attended by every other word in the sentence. The self-attention got its name because the same sequence is referred which is being encoded by the model. But you may ask why the model needs this contextual information at first place. Let me explain it to you. Let us consider these two sentences. I ate an apple and an orange. I use Apple products. Now in both the sentences, we have used the same word apple, but they have completely different meanings based on the context in which they are used. In the first sentence, the apple refers to a fruit, while in the second sentence, the apple refers to a company. So, it is really important for the model to understand the context in which the word is being used in order to provide meaningful information to the user. To understand this behavior, we can look at it in another way, where each word is linked to every other word in the sentence through some weightages. Now these weights could be higher for words like name and Optimus, which is represented by the higher thickness of the line, while it could be lower for the words like hello and is. Now the words containing the higher weightages are linked strongly to each other, while the words with lower weightages are weakly correlated to each other. Now if we look at our transformers architecture, it contains multi-head attention blocks. By that, it simply means that it doesn't form this weight matrix just once, but for multiple times. For example, the first head may form the weight matrix which looks like this, while another head may form weight matrix which looks completely different. The intuition here is that each self-attention head will learn a different aspect of the language. For example, one head may see the relationship between the people entities in our sentence, whilst another head may focus on the activity of the sentence. Also, it is important to note that we don't dictate ahead of time what aspects of language the attention heads will learn. In a simplistic way, we can say that these weights are finally stored in a matrix form, which are then multiplied by the input embedding vector to give us the final context-aware attention vector that we need. If we go into more detail about it, we can see from the paper that they have used scale dot product attention in order to calculate this context-aware attention vector. For this, each word in the sentence is assigned three vectors: the query vector, the key vector, and the value vector. And these vectors are used such that first the query and key vectors are multiplied together through matrix multiplication, and then they are scaled through some denominator value. After that, the values in this matrix are passed through Softmax function such that each value in the matrix is normalized in a way that all the values in a row adds up to 1. Now this weight matrix is multiplied to the value vector of our word. After this, we get the final attention vector. Now in order to get the intuition behind it, let us see this embedding space in two-dimensional. Now from our previous example, we know that we have used apple in two different contexts, but since they are the same word, they are being embedded into the embedding space at the same location. But after learning this attention vector, these vectors would be separated such that the apple, which is used in the context of fruit, is assigned a closer position to orange, while the apple, which is related to company, is assigned closer to the word product. This way, the model creates a meaningful representation of the words in the context in which they are used. Now once we have these attention vectors are then fed to the next component, which is the feed forward network. these feed-forward networks simply outputs the vectors of logits that are proportional to the probability score for each and every token in the tokenizer dictionary. Now if you observe, in the encoder, the output of these feed-forward networks is again passed to the decoder part, which is passed through another multi-head attention component, which is then passed to another feed-forward network in the decoder network. Now, the final output of this feed-forward network is passed to the final layer, which is the Softmax layer. This Softmax layer converts these vector of logits into some probability score, which assigns probabilities to each of the token IDs in the whole English vocabulary. We could use the highest probability to select our output word. So in our case, we have this token ID which has the highest probability. Now remember, in the beginning we used a tokenizer to convert our input sentence into some form of numbers. Now here also we will use the same tokenizer to get our final word output. So the model selects our output word as prime, and this completes the sentence. So this was the whole picture, how transformers take sentences as an input, converts them into some numbers, and then applies some processes, and then finally selects the final token ID and again converts it back to the word using the same tokenizer. Now, whenever we talk about transformers or large language models, there is this upcoming field under the name of prompt engineering. Now, what is prompt engineering? Whenever we want a pre-trained large language model to behave in a certain way for a particular task, it may fail to do so. And for that case, we may have to revise the language in our prompt or in the input in the way that it's written several times to get the model to behave in the way that you want. Now this work to develop and improve the prompt is known as prompt engineering. We'll not cover this topic in this part of the video. Instead, we'll be covering it in detail in the second part of the video. So this was the wrap up on the first part of this video. Hope you learned something valuable today. Soon I'll also be coming out with the next part of this video where we will discuss more on prompt engineering. So do hit that subscribe button and the bell icon so that you get the notification as soon as the video comes out. Thank you for watching.